Jorge, Amaya on parametrization of solar active regions using variational autoencoders. George, are you here?
Yes, can you hear me?
Yes. Would
All
you
right.
please share your screen?
Yes. Allow me.
Okay. Could you try again?
Let me just 1 second here.
Yes,
So
we can see it. Yeah.
you can see it probably right now, right? In the correct.
Yeah. Perfect. Yeah.
Okay. All right. So let me start my chronometer here. So I'm sure that I don't do more than 15 minutes. So here we go. So thanks for accepting my talk. I'm going to talk to you about parametrization of solar active regions using variational autoencoders. But before that, I just wanted to give some words of support. I really applaud this initiative. I have been sharing for many years on the development of better techniques of AI and machine learning for space weather. My first account working with machine learning was 20 years ago when I did my bachelor's thesis. And recently in KU Leuven, we started to work on a group in around 2014, starting to apply machine learning and different aspects of space weather. Of course, the first example that everybody does is to calculate the DST index using the solar wind with neural networks. So what I would like to do now is encourage you to continue to develop more modern and more complex AI methods, because those neural networks we have tried already for more than 20 years. So we can move and do better things now, I believe. One of the things that I believe is going to come in the near future is to include data simulation in physics-informed methods for space weather forecasting, but also machine learning assimilation. So what it means is we are going to be combining machine learning data in the near future to have forecasting tools to become operational. So I do encourage you to keep developing more and keep an eye on the recent literature on machine learning. So what I'm going to present here today is some work that we started a couple of years ago in KU Leuven, and that we continue a little bit to refine here at ESA with some of our interns here. So as everybody knows, this couple of slides that I present here is mainly when I do presentations for space physicists that do not know too much about machine learning. But as you can imagine, I can go through this quickly. The path to apply a machine learning technique is not simply getting the data, apply machine learning and get results. What you find out is that there is this step in between, which is processing, analysis, reworking on the data, projection, extrapolations, etc., that happens way before you start using machine learning. Then you have the step of selecting the best machine learning technique that you want for your data. So it takes quite some time. And that first step is rather an important one. So you have seen already yesterday the presentation from Hanne Beke, who, yes, just before going that, I had this side note because I have been doing a lot of reviews for publications and proposals. So some observations that I have collected over the years during these reviews is that we need to create trustworthy methods. And to create trustworthy methods, you need to provide access to your data sets, access to your source code. Bonus points is to provide a Jupyter notebook that the reviewer can execute and get online and get the results, verify your results, use explainable AI techniques, and show that there is no overfitting. So, and also remember that there is a correct technique for the correct data. So if you use small data sets with a large number of parameters, in general, that's not suitable for a neural network. If you have tabular data, you must always, your first technique to test is gradient boosted trees, which has shown always the best results. LSTMs and recurrent neural networks are used all the time to do time series predictions, but they are very tricky, and you have to be careful on the way that you use because some of them depend on external factors, and then you need a long-term context for these applications. Anyways, that was just a side note to encourage you to use at least some of this advice when you present a publication or when you are applying for a proposal. So what I was going to say is that Hannebeke presented yesterday the first tries that we did in her work on trying to parametrize solar active regions. What that means is that we have solar active regions that we do want to understand if they are active or non-active. And to do that, instead of using the images, we reduce the image to a set of parameters. So that has been done already, is what is called the SHARP database. You have a set of image processing steps that reduce each active region image into just a vector of values. And in this case is, for example, 16 values. So you can apply different machine learning techniques to these values. Now, Hannes showed that this has some difficulties and some complications. We have quite good results, but we can differentiate low activity from high activity flaring active regions. And that's comparable to what we have in the literature. And it's already given quite interesting results. However, what we ended up doing is saying, okay, instead of going through the SHARP database, let's allow the computer to identify automatically what are those parameters for each one of the active regions. Let's reduce that image to parameters that the computer believes are the best parameters for each active region. So to do that, we are using autoencoders. And in an autoencoder, you expect that the input image and the output image is the same, and is a neural network in which in the center you have a bottleneck, and that bottleneck is a compressed version of your image. Autoencoders have been used a lot in different applications, in particular in image applications. It's used for deep fakes, data denoising, style transfer, image super resolution, image segmentation. And we have used some of them for space weather applications. For example, in super resolution to increase the resolution of the sun, of SDO images, or in image segmentation to identify corona holes from non-corona holes. We have used this technique. Now, this is going to reduce your image to a set of a certain number of parameters. And it's not a new idea either. It has been applied before. 2019, we have this paper that was published by Chen et al., in which they use this called vanilla autoencoder, in which in the center, the hidden layer is a matrix of 16 by 8. So it's actually is a total of 512, actually 512 by 16 by 8. So at the total in the center, you have reduced the image into 65,000 features. And then those features are passed through an LSTM to detect what is going to be the status of the active region in the future. And then you see on the bottom left, you see some reconstructions, some original image and reconstructions. So let me zoom in into those images, and you see that the reconstructions are okay, they are not perfect, but at least they kind of follow the general structure of the active region. Now, I think a couple of years ago, we thought that we might do better than this. So what we have been using is something called variational autoencoders. In this case, the bottleneck in the center is become a latent space, which is a continuous latent space. Is a distribution, probability distribution space in which images that are similar are located in the similar locations in the latent space. So it compresses the image into this latent space, which is continuous, and allows to a continuous movement from one image to a similar image. So this is the exact architecture that we have been using since then. We reduce images, we do a pre-processing of some active regions, we do a selection of some of them, and we extract active regions which are of size 128 by 256 and has 3 channels corresponding to the 3 magnetic parameters. Then we reduce all of that to a bottleneck, which is 2 times 8 codes, which corresponds to 8 mean values and 8 standard deviations. And that means that we have a latent space, which is continuous, as it is composed by Gaussians in the center. And what we have on the left, on the bottom left is the original image, and then the bottom right is the reconstruction, which I believe is already a good result. When you look at each one of the components, you see that the results are quite good as well. But what is interesting is that this encoded image in the center is a continuous space. So it means that I can create artificial active regions between two different original images and see how this active region evolves in time. So why is this interesting? Is because then each one of these parameters in the encoded space can be correlated to a physical quantity, like the size of the active region or the polarization, but it also allows you to see what are the changes in an active region that makes it go from non-active to active. And then you can create all those the intermediate steps, because this is a generative technique. So that allows you to study the active region in more detail. So this is an example going from two different one active region on the left, one active region on the right. I can generate all the intermediate steps. You see the changes of polarity, the changes of shape, and so you can follow all of that and study. Now, the other thing that you can do is what I was saying. You can start with an active region in the center. Here is the image in the center, and you can move one parameter up, and then you can move another parameter to the left and right, and you can generate different kind of active regions. This could be also interesting when you have an unbalanced data set of active regions that you want to use for a study of any of your machine learning techniques that you can use afterwards. Now, after working in Q11, I asked one of our colleagues here to take a look at the technique and see, because I was getting some weird behaviors. The behavior is that I was saying we have 2 times 8 parameters, which are here on the left. So this is the full data set, and these are the encoded data in those parameters. So there was one of the mean values, which was completely constant and with a very large standard deviation, which I represent here on the right, meaning that all the data sets were having the same Gaussian distribution in that latent space, which is not what we want. We want that each one of the active regions has a different representation. So I asked one colleague of mine what was going on, and he found out that we have to be careful on the way that we train the technique. So when we produce a change in the training method, which I'm not going to go into the details here, we get much better results. So this is the final architecture. We even reduce the number of latent space to 6 parameters in the bottleneck. And you see the reconstruction from the original image on the top to the reconstructed image on the bottom. The images are much, much better. And this is quite impressive. We are reducing an image of a big size into only 6 parameters. It means that we can represent an active region with only 6 parameters. Why is this important? Is because if you want to perform a classification, like for example, an unsupervised classification, you want to have a latent space as small as possible, because you have to be careful with the curse of dimensionality. When you have a parametrization with too many dimensions, it's difficult to find a distance metric that doesn't put all the points in different locations in space. So the idea of clustering, for example, is to find groups of points which are similar. And that is only possible if the dimensions is as small as possible. So this moving to only 6 dimensions in the latent space is really interesting for future classifications of active regions. So this, of course, is not necessarily applied only to active regions. You can apply to the full solar disk. You can apply to observations of CMEs. You can apply to observations of auroral ovals. So if you want to perform classifications or if you want to parameterize what is that you're looking at. But not only that, you can apply it also to spectra or to time series parametrizations. So you can do analysis of the solar wind, for example, a classification of the solar wind using, as you can see on the bottom right, for example, wavelets, or to classify radio bursts, solar radio bursts, depending on the observation that you have using the same technique. So this can be applied to any data that you can present in an image shape or in a matrix shape. All right, so the conclusion is that the automatic parametrization might require some pre-processing steps, but the variational autoencoder is a really interesting technique that can be used to parameterize anything that is related to images. And it allows also to compress and decompress image and that could potentially be used also on board satellites. And the idea is that we are starting to go further than this. We are not using only HMI images, but we're also adding other AIA images on different wavelengths to improve the detection and the parametrization of the active region to better find these flaring activities. And of course, that gives some information about the 3D structure of the active regions that we could also parameterize. And of course, time series, once you have a parametrization of your active region, you can follow your active region over time and see when these parameters change over time, and that is a clear indication of flaring activity in the future, so you can perform forecastings of flaring or CME creation. So yeah, so that was from my side. I think it's 15 minutes exactly, so if you have any questions, please, now is the time.
Thank you very much, that's perfect. Do we have any question? Okay, yeah.
Yes, thank you, Jorge. This is Manolis. Very interesting talk.
Manolis.
A question I have is, have you tried to, based on your results, have you tried to come up with any metadata of the ones that SHARPs are using or other projects are using, for example, to try to see how the metadata of the the final decoded images matches the original metadata of the magnetograms?
Yeah, we have not done that, but we are working. So I hope that you saw the presentation yesterday from Hane.
Right.
We are working on the same kind of database, and we are comparing those two. So the idea is indeed to check if the sharp parameters are corresponding to any of the parameters in the autoencoded codes. My guess is that if you remember the presentation from Hane, we managed to reduce the number of parameters from SHARP from 20-something down to 5 parameters. And here we have encoded values of 6 parameters. So they might be correlated. So not one-to-one with the SHARP, but maybe one-to-one with the reduced SHARP parameters. That might be something that we can check.
Right. Even if you could correlate between the one and the other, that would be useful, because in this case you would have, at a much smaller volume, you would have an idea of what the actual magnetogram would give you in terms of metadata.
Exactly. And the idea is also that once we have these parameters, encoded parameters, the idea is to move them and to see to what does that correspond. Does it correspond to the shape of the active region, to the polarity, to the size, and see if those also correlate with the SHARP database. Yeah, so that's indeed something that we can look at.
Great, thank you.
Thank you.
Hi, nice talk. I wanted to ask you, why did you choose, is there any specific reason why did you choose VIE for competing on this task? Is it just an evolution of AE, or there is any other, reason behind it?
Yes, there is a reason. We started indeed with autoencoders, so vanilla autoencoders, the basic ones. But there is a couple of problems with that. The first one is the latent space in an autoencoder is not continuous, is discontinuous. So if you have two encoded images and you look at them in the latent space, the space between those 2 points might not be correlated. So everything that you put in between those two images in the latent space might be just noise. And actually that happens very often. You put that code, that in-between code, and then you get noise at the exit. So the advantage of variational autoencoder is that the latent space is continuous. So you can move between two active regions in a continuous way, and in between the images correspond to similar images. The second part is that basic autoencoders don't necessarily put the similar points in similar locations. Variational autoencoders force you to put every similar image in the same location in the latent space. So that allows you later to perform, for example, unsupervised classification that you cannot do in that case with autoencoders. And the third reason is that to get good outputs, for vanilla autoencoders, the bottleneck is much bigger. So we found that around 64 parameters you get with vanilla autoencoders. Variational autoencoders, as you saw, it reduces down to only 6.
Okay, so I have another question if I can. Okay. So yeah, I wanted to follow up on this because I worked with VIE2, and what do you mean with, do you have a metric that says, mathematically speaking, that it improves if you go from, I don't know, it was 2 multiplied by 8 up to 6 in terms of the latent space dimensions? What do you mean in terms of improving? Because you spoke about cluster, the problem, the curse of dimensionality. So you want to cluster on this latent space, visually speaking, or with, I don't know, any particular method?
Let's see. Yes. The idea is that with the autoencoder, what you get is at the end, you get a parametrization of your active region, right? So you want that the number of parameters that describe your active region is as small as possible. So your clustering and classification techniques work in that case. Because if you have too many parameters, classification techniques don't work that well because you have this distance parameter that you have to take care of. And that's the main reason. So I didn't follow up the other part of your question. You were saying that
yeah, basically what I wanted to know if, because in my case, the lower it is, the worse it is. In terms
yeah,
of
that happens all the time. Yeah, definitely, that happens all the time. And so you have a balance between the quality of the image that you output and the number of parameters in the center. So of course, the more parameters you have in the bottleneck, the better is your reconstruction. So we reduce it as much as possible as to the point that we get good results. Now, what we call good results is just visual good results. What would be nice to have, and what we wanted to have at some point is to generate, for example, the sharp parameters from the input and the sharp parameters from the output and compare the values of the sharp parameters. And that gives you a numerical distance between the images to tell you exactly how good of a reconstruction it is. So it's a physical error that you can get because comparing pixel to pixel is never good when you are working with images. You have to use something more sophisticated than that.
I see. Can I have another?
Okay, yeah. Maybe one more question and we can discuss later.
Thanks. So since apparently you want to use the generated images, right? Have you ever also considered on using other techniques such as GANs or diffusion models?
Yes.
Instead of VAE?
Yes, we did use GANs at some point to do super resolution of solar images. And I started doing some work on GANs. So what you can do is that you have this variational autoencoder, and what you can do is you can take the latent space and create a generator, and then work with the generator and the autoencoder to make them fight to get the best results together. So like in a classic GAN. So that is an extended variational autoencoder technique. For the moment, I didn't find that it was so necessary for our goal, because our goal was to produce a latent space parametrization which is interesting for classification. And just by visually inspecting the images, we see that we are producing images that are very similar, which is the important goal right now, is to make sure that our latent space makes sense, and then apply the classification in that latent space. GANs is an extension that I think is going to improve indeed the results. I'm not sure that it's going to, at this moment, I think it's too much work to gain not that much in quality, but yes, that's an option. And let's just remember also that these variational autoencoders can also work as generators. So you can put a random number in the latent space and generate an image, and it's going to generate a proper solar active region. So that's what we do. We do 2 active regions, and we find a point in between the latent space, and we generate from that point, at that artificial point, we generate an artificial active region. So in that artificial active region is very similar to the 2 previous ones. So it is a generator technique in itself. So yeah, we are looking at different possibilities in that sense, yes.
Okay, thanks.
Okay, thank you very much. And we have to move on because we are short on time.
Yeah, thank you so much. So Hannebeke is somewhere in the audience, so if you have more questions, maybe you can ask her and she can ask me later. Thanks anyways.
Okay, thank you.